Today we are going to study about Fourier transform. Fourier transform is closely related to the Fourier series expression. Before that, I'd like to let you know that the sinc function here, sinc function expressed by sine pi t over pi t. From here, that as t goes to the 0, it approaches to unit. And the pattern looks like this one. This is t equals 0 axis. The waveform patterns looks like this one. Okay, this one. At t equals 0, it is 1. And think about the first null. First null is in this moment is t equals 1, and the left hand side is -1. This and also this is 2 and -3, -2, -3, and 2 and 3. It looks like that. I'd like to plot that one with octave. First, make series. Okay, here. Okay, this is command line, and first I create a time series at here. Time series by use of colon, start -5, step 0.1, and up to 5. Then this will create a vector from -1 to 5 time series, and signal can be created from this time series with a sinc function. Sinc function given time like that. Then I can create TS and XS. XS is a sinc function. Sinc function, as I talked to you, that this function. And then I can plot that one with a time versus XS. Okay, let's this one is a sinc function plot. Okay, then I can run it from here. Then I can get this result, and from command window I can a little bit modify that one. Okay, first I would like to over the grid. Okay, then it shows the grid and takes every integer, positive and negative integer. So that one x ticks, it should starting from linear space -5 to 5, 11 point. Then the grid point will follow that way. Okay, this is sinc function. Let's look at here. Okay, from here I plotted the sinc functions, sinc t, like that. At t equals 0 is magnitude is 1, and the first null means the first time it goes to 0 is this point. If this argument equals to 1, in that case sine pi is 0. So this is the first null. The second null is at this point. It's t equal 2, it means sine 2 pi is 0. In between 0 to the pi, sine is positive number. But if between pi and 2 pi is negative, and positive and negative alternating like that. So you need to think about every nulls. I can change the plot here. Okay, look at here. I added grid point and x ticks, linear space -5 to the 5 and 11 point. Okay, I plotted the sinc function, but what about if I plot the absolute value of the XS series with a color red? Okay, then I would like to do that. Then look at here. What's the I overplot the absolute value of that. You can see that this is positive area, but this one is negative, is taking absolute value. It looks like that one. We call this point is null. First null, second null, third null, like that. So first null is very important. So the sink goes to the 0 at this point if the argument becomes equals to 1. Okay, keep in mind that one. So we study about the sink function. The sink function, the first null occurred at this point. So argument becomes 1 or -1 gives the first null positions. And the value at the t equals 0 is also unit, like that. Okay. Now let's review for the Fourier series. Here shows a periodic rectangular pulse. The pulse width is a non-zero value between -tau/2 to the tau/2. This should be positive. So in between this time it's 1. All the other times it's 0. We can take in period from -t/2 t/2. So this is our concerned period. So we only concerned this time. Taking Fourier series expansion, it looks like this one. xt is a periodic signal with a period of t. Then xt can be expanded by Fourier series. xk is a Fourier series coefficient, and this is complex exponential with the harmonics of omega 0. So omega 0 is defined by 2 pi over t. To find out the Fourier series coefficient, we can using this functional dot product. This is signal, and taking dot product with complex exponential with the harmonic numbers k omega 0, then we can get the kth harmonic component. We can take in integration over one period. We take the period from -t/2 to the t/2, then only non-zero between -tau/2 and tau/2. So this integration can be shown here. 1/t, only non-zero between tau/2 and -tau/2. We taking value as 1. It gives like that kind of things. By taking integration with respect to time, it gives this result. We already studied about that one when we handled the Fourier series. At here, omega 0 is this one. Just to replace omega 0 with 2 pi over t. This is also 2 pi over t. 2 pi over t. T is the period. Then 2 and 2 cancelled out. And here also 2 pi over t, then 2 and 2 will cancel out. And j and j also cancelled out. And then the k times omega 0 change the k times pi over t. It means the numerator becomes the k times pi over t. Okay. For t. So this is the numerator. To make it sinc function, we you know that the sign argument are sign at here, the pi are here, and the k tau are shown here, and t are shown here. So this is the x argument, the sign argument. To make a sinc function, we need to multiply tau here and divide the tau here. Then it looks like this one. Then this function are given with tau over t. Okay, sinc function over k tau over t. So the Fourier series coefficient, kth harmony coefficient are given like that. The kth harmony means this one. So I plotted the sinc function over here. So you can see the dotted line is a sinc function. Okay, and the xk xk is given as tau over t times the sinc k tau over t. I said that the first null point, this argument should be 1. To be that, you know that this is k axis, k harmonic index should be t over tau. Okay, then this becomes the 1. So that's this point. Fourier series coefficient shows us the harmonic component, as we know that this axis is a harmonic index. If harmonic index equals to 0, this point is a harmonic index 0 means that the DC component. If harmonic index 1, it means omega 0. The next one is 2 times omega 0 harmonic component. It's the same, minus omega 0, like that. As we know that this axis means that the harmonic index number. Okay, so if you think about the separation of this spectrum, this frequency difference is omega 0. So omega 0 is 2 pi over t. So in the time domain, it has a rectangular pulse repeated every period. But if you're taking Fourier series, it shows that the harmonic component of this Fourier series one. Now think about if t is increasing, what's going to happen? As t increase, this space is narrow down like that. Narrow down. If increasing the frequency step, it means that harmonic step is decreased. I plotted a sinc function with enough the harmonic frequency, the period, enough larger period. So the space between each harmonic index, it's narrow and narrow. As we know that the t increasing, this omega 0 will goes down. So that's this one. So if we increasing, the frequency step is decreasing. It's related to the period. If a period is larger, then this frequency step is smaller and smaller. But what if we taking the t goes to the infinity? So it means it is not periodic anymore. The period is infinity. It means that it is non-periodic. In that case, the xt signal can be think about the non-periodic signal, just a single pulse like that. So period, and you know that this goes to infinity. Okay, then this one is just a single rectangular pulse. It's a non-zero between minus tau over 2. This should be positive tau over 2. Okay, like this one. We call this one is a rectangular pulse. In this case, xt is 1 if t is a greater than minus tau over 2 and less than tau over 2. Then this one is 1. Other case is 0 otherwise. Okay, that's this plot. It has this kind of plot. Okay, like that. But what about in the spectral domain? Let's think about that one. As we increase the t, this space is smaller and smaller. If a period is large enough, the spectral domain is it seems like continuous one. Okay, we would like to think about that behavior. Okay, see here, as I talked to you that if t goes to the infinity, as t increasing, xt becomes non-periodic signal. Now this one. So at the period of t, signal is this one, but the period is large enough, it is non-periodic signal. And another thing is this one, frequency step. So k plus 1's harmonic minus kth harmonic difference is frequency difference. These frequency steps are omega 0, but omega 0 is 2 pi over t. As t goes to the infinity, it seems like a continuous one. We call that this frequency difference 1 over t. You know what that delta omega. Sometimes we call this as d omega. Very small frequency step, I equals to 2 pi over t. That's shown here. Delta omega is 2 pi over t. Then we can think about 1 over t. 1 over t should be equal d omega over 2 pi. Okay. This is shown here. In the Fourier series, in the periodic domain, Fourier series coefficient can be found from these equations. 1 over t and taking one period and periodic signal times basis function and taking integration over the one period. But the period goes to the infinity, then the integration domain goes to the minus infinity to the infinity, and 1 over t should be replaced by d omega of 2 pi, and the integration ranging from infinity range. And xt is not anymore periodic, so we replaced xt. The basis function now, n omega 0 becomes the omega, okay? K omega 0, kth harmony is given as omega. So we just replaced n omega 0 with the omega, and it becomes like this kind of equations. In these equations, we defined this block with xj omega. So xj omega are given like that. So the xj omega is corresponding this part. So this part can be represented by this way, by multiplying t left hand side. Then it, as t goes to infinity, this part corresponding to this one. That is called Fourier transform of xt. This is called Fourier transform. Okay. We defined the Fourier transform, but still we need to go the inverse Fourier transform. Fourier series expansion are given like that. But what will be the expression for t that period goes to the infinity? This one should be approached to xt as t goes to the infinity. And xk should be approached at this value. Okay. This one is d omega over 2 pi times xj omega are corresponding this part. Okay. Compare the relationship between the periodic one and the non-periodic one. You know that xk corresponding this one. As t goes to infinity, it should be looks like this one. That's this part. So that's the xj omega and d omega over 2 pi are given here. And e to the j k omega should be replaced by omega. So that's this one. Figure out the relationships. This one becomes this one, and xk are this one. Okay, xk are is this one, and the k omega is omega. Then xk is xj omega times d omega over 2 pi. That's this one. So let's redefine the Fourier transform and inverse Fourier transform. The Fourier transform of xt is expressed by this one. This is called we call Fourier transform over xt. Is defined by okay, let's change this one. Is infinity to infinity. Xt e to the minus j omega t and taking integration. Okay, this is called Fourier transform. The inverse Fourier transform are defined by x j omega d to the j omega c dot t over d omega. Okay. We talk about the relationship between the Fourier series and the Fourier transform. In the Fourier series, it's a periodic function, but taking period as infinity, we're taking the period as infinity, it becomes the Fourier transforms. Fourier transform is related to the Fourier series coefficient. Fourier series coefficient is calculated by this one. You know that the 1 over t is d omega of 2 pi, and t goes to infinity, then the integration range should be infinity, and this becomes the non-periodic xt, and n omega 0 means delta omega 0, that's this one, okay, times n. We replace this one is omega, so omega is a continuous variable. Okay, now as t goes to infinity, delta omega goes to the 0, so omega is a continuous number, and dt are given here. So we defined the red block, this one, as a Fourier transform. Okay, this is Fourier transform, and the similarity between the Fourier series and the Fourier transform, we can find out the inverse Fourier transform. As t goes to infinity, xtt becomes the non-periodic signal, and the Fourier series coefficient xk can be replaced by d omega over 2 pi times xj omega. Xj omega times d omega 2 pi. This corresponds to this Fourier series coefficient, and the basis function are given here like that. So we define the Fourier transform. Xt is a non-periodic signal. This waveform take the dot product between the complex exponential basis function by use of this integration, that is Fourier transforms. And to take an inverse Fourier transform, we are using the d omega over 2 pi and integration the whole range. Okay, so I hope that you have some idea about the Fourier transform and how it is related to the Fourier series.